So this is a follow-up to my Advent of Code Day 8 2021 Part 2. We're going to delete everything we have, and we're going to do this using the technique that you would have seen me think about for a while, where I was thinking about the intersections of different bits of the puzzle and trying to sort of combine them all together. So now what we can do is, this is going to be our full solution. The first thing we need to do is we need to acquire, in fact, let's explain the solution. So we know the following just from our wire length. Which is there's a way to subscript, right? Not really, okay. I will build a digraphs map at some point, but for now, let's say the length of our wire, WL. This gives us that with a wire length of 2, and we have 1 with a line, and I'm going to call that I'll just call it 1 for now. With a wire length of 3, we have 7. With a wire length of 4, we have 4, and with a wire length of if we know there's 7 segments, then we have 8. Okay. Now, what we can do is we can look at WL. We can look at W's union with 7, and we can look at W's union with 4. And this lets us produce some more unique results. So the first thing we need to differentiate is where it is 5. So where it is 5, there's 3 possibilities. It can be 2, 3, or 5. Where it is 5 and it has a union length, we should specify these are all the lengths. When it has a union length of 7, so basically they intersect each other, like 7 is contained within the symbol, then it can only be oh wait, hold on, for a length of 5, yeah, if it contains 7 it can only be 3, because if you think about it, 2 and 5 don't contain that bottom right segment, and if it contains 5 it does not contain 7, but it intersects 4 in 3 places, then it must be 2 places, 5 intersects it in 2 places. Yeah, so here, rather than intersecting it, well, so here it intersects in all 3 places it can intersect. Here it only intersects in 2 places. If we then have 3 intersections with 4, think of how 4 is displayed. It'll be the left, the mid, and the bottom right. Top left, middle, and bottom right. Then we have a 5. But if we have 2 intersections with 4, then we have got a 2. Now, likewise for 6 could be 0, 6, or 9, but we can use these other 2 again to differentiate them. So if it is intersection with 4 is all of them, so 4, then we know we have a 9, because 6 and 0 don't contain, 6 doesn't contain the top right, and 0 doesn't contain the middle. If then we have a intersection with 7 and 4, with 7 and not 4, it only has 3 or 4, then we know we have 0. And if we have 6 here, we have 1, 2, 3, sorry, contain 7 is 3. We have only 2 here, and we have 3 here. 1, 2, 3, yep. Then we know this is a 6, and so that disambiguates the numbers we don't know. So all we need to do is start by saying let, now we only actually care about 7 and 4 is going to be input, so again, this is going to be input.wires, input.segments, iter sum, iter map sum. That is going to be our overall format. Now the map is where the interesting things happen, so this is a segment. Now, for each of these, the first thing we need to do with our segment, which I'll remind you is just a bunch of these, is we need to look at for each segment, we need to look at the full cycle, and we need to extract from it. We need to know what 4 and we need to know what 7 and 4 are. Now, the way we do that is we extract from it the ones that have length of 7 and a length of 4, which we can do by saying segment.fullCycle .iter .map n.len, so now they're represented as their lengths, or rather yeah, we want to do iter map, and we want to have them not only have their wire, but also we want to include the length. So that adds the length in as information that we're privy to. This should just be an equals. Put a 0 here for type checking purposes. Yep. Now, from inside that map, we want to say we want to fold, and we start with none, none. We have 7, 4, and then we do not care about the item, we only care about the length. And our length in here, we want to say if n is equal, so 7 is when there is 3 of them, then we return, actually I guess we can say item. We can say sum item 4. Else if n, let's do it in a match. We'll say match n. So if n matches to 4, it matches to 3, then we know we have some item. We found 7, we still need to find 4. If it is equal to 4, then we have some. Then we have 7. We have some item. And then if it is equal to anything else, then we just continue our search for 7 and 4. Okay, so that will find our 7 and our 4. But we don't quite want 7 filter map. We don't quite want 7, 4 in that format. We want them in the format 7, sum 7, 4. And we can unwrap them internally. So that kind of is going to unwrap our elements. Okay, no. Okay, so then we're going to say let 7 equal 7. Let's filter map here. Let 4 equal 4. Okay, so that's going to give us our 7 and our 4. It's annoying that there's no way to kind of do that here, but that gets us our 7 and our 4. Okay, now we have our 7 and our 4 found, so those are both located segment instructions. Let's actually look at the wires on them. So that is the segment instruction wires for 7 and 4. Okay. Now, what we can do is we can match. We want to match carefully here. Well, hold on. We want now we need to do that whole sort of stepping up powers of tens thing that we had before. So that is segment.output.iter.rev.fold. Sum this, and we start with 0, and then we start with 0, and we call that pow, and we need to scan, not fold, and then sum. Okay, so we start with 0, and we say 10 u32.pow. We have our power and we have our item. Of pow times by item, pow minus 1, because we need to do pow plus equals 1. So that is our scan reduce. And we don't want to do item, we want to do match, and now here is the clever part. So we have item.wires.len, that's our first field. Then we have 7.intersection. So we want the intersection of 7 and item.wires.count and the intersection of 4 with item.wires.count. And the error we have encountered here is a lack of curly braces. Okay, so now we have down here our possibility. This is where our possibility space goes. So let's start with the easy ones. If you only have 2 elements, then you are a 1. If you only have 3 elements, then you are a 7. If you have 4 elements only, then you are a 4. And if you have 7 elements only, then you are a 7. Nice and easy. Oh, sorry, if you have 7 elements only, then you're an 8. Nice and easy. 1, 7, 4, 8. Okay. Next up, if you have got 5 elements and you intersect with 7 in 3 places, then you are a 3. If you have 5 elements, you do not intersect with 7 in 3 places, but you do intersect with 4 in 3 places, then you are a 5. Otherwise, you are a 2. If you have 6 of them and you intersect with 4 in 4 places, then you are a 9. If you intersect with 7 in 3 places, then you are a 0. Else, you are a 6. That there is our sum. And this inner sum we can get rid of by replacing this with a flat map and then not summing here. And then we can remove the wrap, and then we'll leave the wrapping sum in. Oh wait, no we can't, because the flat map, we need the option wrapping it. So you're fine, and then in here we just need to annotate you as a sum of U32. Okay, now what does it not like? Sum U32 is not satisfied. It should be. Right? What's the error? These are being assumed to be a U32 for some reason. Why are these being interpreted as a U32? Oh, I see. It's that I said the function returns a usize. We can make that. We can make it a usize. Nothing in here needs to be a U32. That's just what I kind of reached for on instinct. There we go. Okay, and now you don't like that it's 10 U32, so let's just let it infer that it's a usize. Cool. Okay, so now what's your issue? No diagnostics found. Test. Passes. Completes substantially faster. And just to show you that that was my original advent of code solution, see it highlighted there.